Now that we have Newton's three laws of motion down, and I'll remind you again that Newton's three laws of motion are basically the rules that forces have to obey. So now that we know what those rules are, we're going to spend the next few lessons talking about some specific forces and how those specific forces behave and how we can solve problems to do with those forces. But all the while, keeping in the back of our minds Newton's three laws, these three laws that our forces have to obey going forward. So the first force we're going to dig into a bit is the force of gravity. It's one that's come up quite a number of times already. And surprise, surprise, the scientist who's credited with developing one of the major theories we have today for how gravity works is, again, Newton. So this guy did a lot of stuff in this field. So in addition to his three laws of motion, we also have Newton's universal law of gravitation. Now, when a lot of people think of gravity, they tend to just think of the force that pulls you down to the earth. And yes, that is gravity, but gravity is so much more than that. Gravity is a force that attracts every pair of objects in the universe. And that's a pretty bold statement. What I like to say to students is, think of one object in the universe, any object in the universe. Maybe it's your right ear. Then I say, think of another object in the universe. Maybe it's a speck of dust on Mars. Okay? Your right ear and a speck of dust on Mars are a pair of objects that are in the universe. That means gravity is causing them to feel attracted to each other. Your ear is getting pulled towards that speck of dust on Mars, and that speck of dust on Mars is getting pulled towards your ear. Now, just because your ear is feeling a pull in that direction doesn't mean your ear will actually move in that direction. There's other forces at play that stop your ear from moving. And a good way to remember that is, if you've ever been part of a tug of war, especially if you've been on the losing side, just because you're pulling on the other team, just because you're pulling them in a direction towards you, doesn't mean they're going to actually move towards you. So your ear is getting pulled by that speck of dust on Mars. That speck of dust on Mars is pulling your ear. And that same thing is true for every pair of objects in the universe. One of the reasons why your ear doesn't feel a painful tug from that speck of dust on Mars is because of how gravity works. And there's two things actually at play there. That speck of dust on Mars is A, very small, and B, it's very far away. And because of those two things, you hardly feel that pull at all. So it's worth noting that the strength of gravity depends on the masses of the two objects and the distance between them. So your ear and that speck of dust on Mars, they have pretty small masses and they have a very big distance between them. So they're going to feel a very small force of gravity. Coming back to the Earth, this sort of explains why so many people just default to this force from the Earth when they think of gravity. If you look around you right now, you probably see tons of objects that are actually pulling on you through the force of gravity. Maybe there's you have a screen in front of you. That screen is pulling you towards it. You have maybe a chair beneath you. That chair is pulling you towards it. Maybe you've got some doors or a window to your left or your right. Those objects are pulling you towards them. But because those objects have very small masses, that force of gravity isn't very strong. If you want to feel a force of gravity, you want a force of gravity that's really noticeable, you need to find an object with a very big mass and an object that's very close by. And most of us will go our whole lives where there is only really one object we'll ever come near that is very massive and very close by. And that object is planet Earth. So when you look at all the things that are close by to you that could potentially exert a noticeable force of gravity on you, the only one with a really, really substantial mass is the Earth. So that's really the only force of gravity that you are aware of or that you feel for most of your life. Okay, so what if we want to actually attach some numbers to this, right? How many newtons is Earth pulling on you with? How many newtons is that door beside you pulling on you with? So if we want to calculate how strong this force is, in other words, we want to calculate its magnitude, we can do so using the following equation, which is Newton's universal law of gravitation. Fg equals m1, m2, big G divided by r squared. Now let's unpack this equation. Fg is the force of gravity, or the gravitational force, and it's measured in the metric base units of force, which are newtons. Now remember I said in order for there to be a gravitational force, we need a pair of objects. Well, m1 and m2 are the masses of that pair. m1 being the mass of one of the objects in the metric base units for mass, which are kilograms, and m2 being the mass of the other object. So this might be you and the planet Earth, if we're talking about how hard Earth is pulling on you. Or it might be your ear and that speck of dust on Mars, if that's the force we want to calculate. One thing worth noting here is it doesn't really matter which object you say is m1 and which object you say is m2. Because we're just going to take those two numbers and multiply them anyways, the order here doesn't matter. If I get these backwards, that's fine. Right? 3 times 5 is the same as 5 times 3, as an example. However, so that we can follow each other's work when we're solving problems, it is nice to kind of have a convention. And the convention I like to use is that since 2 is bigger than 1, I usually make m2 the bigger object and m1 the smaller object. So if I'm talking about the force of gravity between me and planet Earth, well, planet Earth is the bigger object in that scenario. So I'd call Earth m2, and I'm the smaller object, so I'd probably call myself m1. But again, if you switch them up, put them in the other order, it's still going to be fine. We also said the distance between the objects was really important, and that's what this r is down here. R is the distance between the object's centers. And this centers part is very, very important. We'll get back to that in a second. The reason we use R here and not D is because in a lot of applications of this equation, we're talking about, say, orbits of planets, things that move in circles. And in that case, R ends up sort of meaning radius. But in a more general terms, we're really just talking about the distance between the centers of these objects that are feeling pulled. Again, the units, we're going to use the metric based units for distance, which are meters. Okay, there's one final letter in this equation that I haven't talked about yet, and it's the one that you probably haven't seen before in this course, and it's this guy up here, this capital letter G, which we call big G. That is the universal gravitational constant. So let's unpack that. Constant means it's the same. It doesn't change. Gravitational means it has to do with gravity, so it makes sense that it's in this equation. And universal meaning it applies in this universe. So this is a number that is constant everywhere in our universe. And I often like to think of big G as a number that tells us how strong gravity is compared to other forces, like the electromagnetic force. So how strong is gravity compared to the electromagnetic force? Well, it's actually really, really weak. Big G in our universe is 6.67 times 10 to the power of negative 11. And I'll remind you that when we raise 10 to a negative power, we're talking about a number that's very small. This means there are many, many, many zeros after the decimal before we get to 6.67. So what I take from this is that gravity is actually a very, very weak force. There's a similar number here called K that tells us how strong the electromagnetic force is. And it's a much, much, much bigger number than this. Okay, the last thing we should talk about is the units of big G. And I could leave this to you for as a quick exercise. you'll recall that just the same way we can do math with numbers, we can do math with units. So if I wanted to find a number for big G, I could plug in numbers here and here and here and here, and I could solve for it. If I want to find the units of big G, I can plug in units here, 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 isolate big G, and solve for it. And here I have kilograms, kilograms. Here I have meters. Here I have newtons. So the units from big G are going to combine all those. And it turns out big G, if you were to isolate big G, rearrange this, plug the units in, you'd find that big G has units of Newton meters squared per kilogram squared. Definitely a bit of a mouthful. So big G is a number. That number is going to be the same in every physics problem you solve in our universe. And that number is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. There's another way you can express these units too, but we'll leave that for another time. OK, so let's take this information and this equation, and let's try putting them to work. Here's our first example. An astronaut at an altitude of 5,000 kilometers experiences a force of 215 newtons from the Earth. So this is the gravitational pull that Earth is exerting on this astronaut. What is the astronaut's mass? Okay, so I think it's always a good idea to draw a tiny diagram. In this question, our diagram is actually going to be fairly useful for one or two reasons. So here's my starting diagram. I've got this circle down here representing the Earth. I've got this little astronaut up here. This is not to scale by any means, but bear with me. OK, so what can I add to this diagram based on what the question gives me? Well, the astronaut has an altitude of 5,000 kilometers. Now, altitude is the distance something is above the ground. If you're flying an airplane, sometimes the pilot will announce your altitude, how many feet you are. That's above the runway, above the surface of the Earth. So let's add that to our diagram. There's the altitude, the distance from the surface of the Earth, from the ground to the astronaut, and it's 5,000 kilometers. And I'm hoping that as soon as you saw this number, 5,000 kilometers, a little bell went off in your head saying, oh, that's not metric base units. I'm probably going to need to convert that. And indeed, we're going to need to do that. Let's just do it right away. 5,000 kilometers can also be written as 5 million meters. And there it is in metric base units. Now, right away, I see we're going to need a little more information. Because we said that the force of gravity between the astronaut and the Earth depends on the distance between the object's centers. That's not what I have here, right? The center of the Earth is down here. This altitude number only takes me to the surface. So if I want to know how far the astronaut is from the center of the Earth, I'm going to need to know this extra bit here. And that extra bit, you might notice, is Earth's radius. I haven't given this to you in the problem, but this is a number that you're going to use again and again. Good physicists just have this number in their head, ready to go at a moment's notice. And I'm going to give that number to you right now. So Earth's radius is 6.38 times 10 to the 6 meters, or about 6,000 kilometers. I've written it down here. I would say keep this page handy because you'll probably need to refer to this number in the coming lessons. Also, I've given you this number on your formula sheet down at the bottom. You can find it there. Another number, while I'm in the mood of giving you stats on Earth, is Earth's mass. We'll actually need that again in this problem. And that is 5.97 times 10 to the 24 kilograms. Now, side note, saying 5.97 actually feels very weird to me because when I grew up in high school and in university, for the large part, I always was told that Earth's mass was 5.98 times 10 to the 24 kilograms. But if you go out on Google and you look up what the Earth's mass is, you will see a number of very reputable sources claiming that Earth's mass is 5.97. So I'm trying to retrain myself to say 5.97. I dug into this a little bit, and I can't figure out why we used to use 5.98, or I used to use 5.98, and now we're using 5.97. I don't think that the Earth's mass is getting smaller, at least not at the rate that change would suggest. It could just be that we now have more precise ways of measuring Earth's mass, and turns out we were a little bit off the first time. But actually, if any of you are slightly curious about this, I'd love for you to dig into it a bit and see if you can let me know, why did we used to use 5.98 and how come we're now using 5.97? I'd be really curious to know. Okay, back to this question. So here's my astronaut. His total distance from the center of the Earth is this plus this. He's feeling a pull of 215 newtons, pulling him down towards the Earth, and we want to know his mass. So let's pull up that equation that we just learned, Newton's universal law of gravitation. Here it is. So the force of gravity felt by the astronaut depends on the astronaut's mass, the Earth's mass, big G, and the distance between the astronaut and the Earth squared. First thing I've done here is I've said, okay, what's the thing I'm actually looking for? That is the astronaut's mass. So what's the astronaut's mass in this equation? That's m1. So I've just isolated m1 in this first step. Now I'm ready to probably plug some numbers in for Fg, for R, for M2, etc. And there we go. Fg, the force of gravity felt by the astronaut, was 250 newtons. So I put that in here. R, the distance between the centers of these two objects, is going to be the altitude plus Earth's radius. So here is the altitude in metric base units. Here is Earth's radius in metric base units. And I'll warn you, the number one mistake that students make when they're working with Newton's universal law of gravitation is this squared here. They always forget to square R, right? They'll write it in the formula, and then once they plug numbers here, there's just so many exponents going on, and there's so many numbers being added and multiplied together that they just forget about this little squared, and that messes up the answer big time. So be warned. Okay, so this R, the distance between the two objects, is going to be the radius of Earth plus the altitude, right? This plus this. Then I have M2, right? The mass of the Earth. And that's here. That's the number I gave you in metric base units. And then we have big G, this number that's always the same everywhere in our universe, 6.67 times 10 to the negative 11. So if I plug all of those in, it should tell me what M1, the mass of the astronaut, is. And you get 69.9 kilograms. At this point, I would really encourage you to pause the video, get out your calculator, and plug all of this in and make sure you can get this number, 69.9. It might seem trivial. All we got to do is multiply and add a few numbers. But I would bet that most students are not going to get this right on their first try. There's a lot of little intricacies here. One piece of advice I'll give you, I already told you to watch out for this squared. Another piece of advice is watch out for brackets. We need to add these two numbers together before we multiply by this one. So having brackets around those two on your calculator will help. Another thing is these two numbers need to be multiplied together before we divide them into the numerator. And if you think you're having a bit of trouble with this, easiest way to do it is do the numerator on your calculator, hit equals, get a number. Do the denominator on your calculator, hit equals, get a number. Then take those two numbers that you've hopefully written down, divide them. It's great if you can do it all in one step on your calculator, and I encourage you to try that. Last piece of advice I'll give you is with regards to scientific notation. There's a lot of scientific notation here, 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 and that's not going to go away for the next couple of lessons. Typing that into your calculator can be a bit annoying, and B, kind of error prone. If you go and you type, for example, with this number 6.67, and then you hit the multiply button, and then you type the number 10, and then you hit the exponent button, and then you try and type 11 and you make it negative, and then you try and take that and multiply it by this, and then you divide it into that, you are setting yourself up for some big mistakes. However, your calculator probably has a button on it that'll make your life way easier here. So here's a calculator tip to help you. My calculator tip is, we'll scroll down a bit, a few different ways to enter, for example, this number or any number that's in scientific notation into your calculator. And what I want you to do is look for one of these three buttons on your calculator. Either a button that says EXP, a button that says EE, or a button that says times 10 to the power of something. All of these three buttons do exactly the same thing. They just look slightly different on different calculators. And what these buttons do is they replace the phrase times 10 to the power of. So for example, if I want 6.67 times 10 to the power of negative 11, I can just type this, 6.67, hit this button, which means times 10 to the power of, and then type in negative 11. Right? Or if I have this EE button, 6.67, EE button, negative 11. Often when people are starting to use this button, they will use it in addition to other things. So people might say 6.67, then they'll hit the times button, which they're not supposed to do, and then they'll hit the exponent button. You don't need to hit the times button. In fact, you don't want to. You don't want to hit any power buttons after this. This one button does the times, it does the 10, and it makes the next number an exponent for you. So it's three things in one. And using this button will prevent you from making a lot of errors as you're typing stuff like this into your calculator. So type this into your calculator. Use one of these three buttons if you can find it on your calculator, and make sure you can get 69.9 as the answer. All right, the next example. 3 objects, each with a mass of 10 kilograms. So 10 kilograms, 10 kilograms, 10 kilograms, are placed in a straight line as shown below. What is the net force on the center object due to the other 2? This part means only look at the forces this object would feel from this object and from this object. Don't look at any other forces that might be at play. So maybe you think this object is sitting on a table and there's a normal force. Don't worry about that. Maybe you think this object is close to planet Earth and there's a gravitational force pulling it down. Don't worry about that. We're just looking at the net force due to the other 2. So first of all, so I can get these objects straight in my head, I'm going to label them A, B, and C. Next, as you should always kind of be in the habit of doing whenever you have a problem involving forces, is I'm going to draw a free body diagram. So there's my object, the center object, the one that I'm interested in looking at the forces on. And I have 2 forces acting on it. Right? This object is getting pulled by this object through the force of gravity. And this object B is getting pulled by this object through the force of gravity. Here's a pair of objects, they're attracted by gravity. Here's a pair of objects, they're attracted by gravity. So B feels a force to the right from C, and it feels a force to the left from A. I'm going to draw those 2 forces. And what I'm going to try to start doing from here on in the course is I'm going to try and draw these forces accurately on my free body diagram in a way that shows where they act. So C, let me ask you for a second, which part of object B is object C pulling on? In reality, object C is pulling on all of B. It's pulling on this chunk of B out here. It's pulling on this chunk of B down here. It's pulling on the center of B. It's pulling on this chunk of B out here. So because this gravitational force is pulling on all parts of B, I kind of just average that out and say it's pulling on the center. And similarly, the gravitational force from A is pulling on every single part of B. So I average that out and I say it's pulling on the center of B. So I have both of these forces pulling on the center of object B. And that's kind of where the phrase center of mass comes from. Or at least that's one of the ways in which it's used. So this force acts on B's center of mass, and this force acts on B's center of mass. I said these two forces are gravitational forces, so I would probably label them Fg. But because I have two of them and they're both slightly different, I'm going to label them FgC and FgA. So force of gravity from object C over here, and force of gravity coming from object A over here. And you'll notice one thing I've done, and I really hope you guys do this on your free body diagrams too, is if I know right off the bat that one of these is bigger than the other, I'm going to adjust the sizes of my arrows to represent that. So because these two are closer, 40 centimeters, than these two, I know this gravitational force is going to be stronger. So I've drawn it with a bit of a larger arrow. OK, so what am I asked to do here? I'm asked to find the net force. So let's start with that. The net force, or the sum of all the forces, I'm going to find by basically writing down every single force and then adding them together. And the way I like to think of doing this is I say, OK, I have two forces, FGA and FGC. Right? There's FGC, there's FGA. And without even thinking about plus or minus or direction, I just write down all the magnitudes. Then I go in afterwards and I say, OK, what are their directions? Well, FGC is going to the right, so I put a positive in front of it. FGA is going to the left, so I put a negative in front of it. Now I've incorporated the magnitudes and the directions of both of those forces. And that's kind of why I like this vector hat here. It reminds me I'm working with vectors, and magnitude and direction are both important. Next step. OK, how could I get a number for FGC and FGA? How could I actually calculate what those are? Well, that's where our equation from the previous page comes in. Force of gravity can be calculated using m1, m2, big G over r squared. And that's the same for both. However, in these two situations, m1 and m2 are slightly different. If I'm looking at the force from object C, then m1 and m2 are the mass of B and the mass of C. If I'm looking at the force that this guy feels from object A, then m1 and m2 are going to be the mass of A and the mass of B. So in my next line, I'm just going to be a bit more explicit about that. Here, I'm looking at the mass of B and the mass of C as m1 and m2, so the force between those two. And here, I'm looking at the mass of B and the mass of A as m1 and m2, so the force of gravity between those two. Now, you might have realized that this is actually a moot point because in the end, every single mass here is 10 kilograms. So in my next line, I'm just going to plug in 10 kilograms for every single m I have. So 10, 10, 10, 10. Also for big G, I've plugged in that number, 6.67 times 10 to the negative 11. And there it is again. And for R, I've plugged in my numbers too. So this R between B and C, the center-to-center distance between B and C was 40 centimeters, and the other one was 50. Now, remember metric base units, so that 40 centimeters is really 0.4 meters, and this 50 centimeters is really 0.5 meters. And those appear down here, 0.4 meters and 0.5 meters. Finally, if I crunch all those on my calculator, and I'm careful about dealing with fractions, and I'm careful about using that button to do this scientific notation, and I remember to square these numbers on the bottom, A lot of things to remember here. Then I should get 1.5 times 10 to the 8 newtons, or positive 1.5 times 10 to the negative 8 newtons. And the way I like to write this down at the very end is, rather than just leaving it as a positive, which is great if you're working with numbers on a calculator, but for human beings, we like to be more explicit in our direction. I would just say 1.5 times 10 to the 8 newtons right. So instead of saying positive, I say the actual direction, and it's to the right. So there you have it. The net force that this object feels due to the gravitational pull from this one and from this one is 1.5 times 10 to the negative 8 newtons to the right. Overall, it's feeling a bit of an excess pull in this direction. And if you want to know how big that is, well, remember that 1 Newton is about how hard you have to push to hold a small apple in the air. So 1.5 times 10 to the negative 8 newtons is a vanishingly small amount of force. You would not be able to detect this if it was exerted on.